of modular invariance. So you remember at the end of the last class we had written down, we reminded ourselves of this formula for we'd reminded ourselves for the formula for the characters of the minimal models. Okay, and this formula was somewhere. Sorry, just 1 minute. Yeah. We had a formula which was chi of lambda. Okay. So what we really had was chi of r comma s. There's also p and p prime floating around here. So which theory, which character? And we wrote this down. Was equal to k of rs minus k of r minus s. Okay, where k of rs was given by the following formula, was 1 by eta of tau, sum over n belonging to integers, q to the power n plus lambda, the whole thing square by 2n. And you remember n was equal to 2p p prime. And lambda was equal to pr minus s p prime. Okay, so this was this very explicit formula for the characters of any representation in a minimal model. Okay, now notice I'm going to do a few sort of quick manipulations. Notice that this formula depends on r and s through the quantity lambda rs, which we've just written down here, which is pr minus sp prime. Okay. Now, I mean, okay, it's not very important, but there is this. Go on.
Just a reminder, so this partition function calculated in terms of these characters.
The partition function is a product of chi and chi bar with some matrix. Okay, and we are trying to constrain that matrix. That matrix is made up only of numbers, of integers, positive integers, because you put some module and some holomorphic module and some anti-holomorphic together. Okay? Okay. Excellent. So now let us look at these. It's not very important, but anyway, let me follow this. The yellow book does the following manipulation. Apart from KRS, we have KR of minus S. Okay, so we get this other quantity, lambda tilde, if you want, which is RS, which is equal to PR plus SP prime. Okay, now it's not particularly illuminating, but let me just follow some of the algebra that the yellow book does. Okay, what the yellow book does is define the following thing. What the yellow book does is define the following thing. The following omega naught as follows. Okay, defines a quantity omega naught which is as follows. First, given any two integers p and p prime, there are always unique integers such that p r naught minus p prime s naught is equal to 1. Given any two relatively prime integers p and p prime, you can always find two integers such that this difference is equal to 1. This is some famous theorem of mathematics, okay, and you can check it yourself. We actually talked about it in the last cycle of the course. Okay. Now, so given any p and p prime, we have an associated r naught and s naught. Okay. Now we define the following quantity. We define this omega naught to be p r naught plus p prime s naught. Okay, we define this quantity for the reasons that you will see. This quantity is only marginally useful, and I debated whether talking to you about it or not, but let me just. Okay. We define this quantity, omega naught is equal to this. Okay. Now I'm going to use omega naught to, the point of this omega naught is that it will give you another way of reversing the sign of R. You see, we have a K with Rs, sorry, reversing the sign of S. We have a K with Rs and another K with R and minus S. Okay? And we want to deal with the Rs and R minus S on equal footing. Okay? So, I'm going to explain to you what the use of this omega naught is in just 1 minute. But as preparation for that, let us note the following facts about this K. Okay? That K up there is defined there. And so now I want to claim the following. I want to claim that if I take, so suppose now I think of K as a function of lambda, not of R and S. Okay? So I first want to claim that K of lambda is the same as K of lambda plus n. Okay, this is an identity. Claim. Why is it true? Well, you see that the definition there involves sum over all integers little n. So suppose lambda was shifted by lambda plus n. Then, let me just write it out. It's just changing the summation variable, right? It's obvious, but let me write it out. Okay? So we have K of lambda plus n is equal to 1 over eta of tau times sum over n belongs to z, q to the power n into n plus 1 plus lambda. Because I've just substituted lambda goes to lambda plus n. Okay? And now I change my dummy summation variable to n plus 1, which also goes over all integers. So it's the same as K of lambda. That's clear? Second thing I want to claim is that this is also equal to K of minus lambda. Okay? Why is that true? Same proof, same kind of proof. I mean, here, this was square, that's really important. We have K of minus lambda is equal to 1 over eta of tau, summation n belongs to z, q of n into n minus lambda, the whole thing squared by 2n. Okay? But now, because it's square, we can make this plus lambda and make the minus here. And then we're summing over all integers. So we make the change of variables, n goes to minus n. If you're summing over minus 1, 0, 1, same as summing over 1, 0, minus 1. Okay? So this quantity K here obeys these useful properties. K is this. Okay? Now, so very roughly speaking, we can ask how many distinct K functions are there? Okay? We can ask how many. Remember, this lambda is some integer. And if we shift the integers by n, we don't get anything new. We take lambda to minus lambda, we don't get anything new. So very roughly, we get n by 2 such distinct functions. Maybe n by 2 plus 1, n by 2 minus 1. You have to do that a little more carefully. But very roughly, n by 2 such functions. You can do that thing more carefully. Just a point. This is clear? So these Ks, there are n by 2 distinct Ks. Okay? But I'm now going to explain, because we don't have just, this character is not just K. It's K of lambda minus K of this lambda tilde.
K doesn't have any other restriction, like there was some restriction on this R and S as functions of P and P prime.
These R and S as functions of P and P prime. there are actually, if you count the number of independent characters, again ignoring shifts by 1, that's n by 4. Okay? So all of these characters will come once I put the next thing in. We've already got n by 2. So this is what we're going towards. Right? Are we? There are all these independent functions, just as k functions, there are about n by 2 independent ones of them. Is each of the independent ones a character? There are twice as many k functions, but exactly as many k minus k tilde. K of lambda minus k of lambda tilde. So to understand the second point, it's useful to look at this omega function. Okay?
What is K as in terms of these blocks of, like, is there some physical thing?
No, K is some.
K2,
K is something that helps you build the block.
the character.
Right, build the character, right. Okay, so the character is the fundamental thing. K is something that helps you make the thing. Okay, excellent. So in order to get that second cut down, it's useful to look at this omega operation. Okay, so there are 2 or 3 identities we're going to try to prove about omega. First thing I want to show is that omega naught squared is equal to 1 mod n. Okay, mod n is going to be of relevance to us because we're going to use these operations like omega naught squared inside acting on lambda inside this character formula, and we've seen that the character formula doesn't change when lambda shifts by something which is a multiple of n. Okay, so identities that are mod n will be useful to us in what goes forward. Okay, so first I want to claim this. Why is it true? Well, it's true for obvious reasons. Let's just write it out. Omega naught was equal to p r naught by plus p prime s naught. Okay, but p r naught minus p prime s naught by definition was 1. Okay, so this was equal to p r naught minus p prime s naught. Okay, plus 2 p prime s naught, for instance. No, maybe I'll do it for the square. Let me do omega naught square. So omega naught square is this thing square. Okay, so omega naught squared is this thing square, but 1 square is equal to p r naught minus p prime s naught, the whole thing square. Okay, and therefore omega naught squared minus 1 square, is equal to 4 p prime s naught r naught. But 2 p prime was n, and therefore omega naught squared is equal to 1 mod n. This clear? This is important because it's going to show us, that's always sort of obvious. Anyway, it shows us that the operation of multiplying by omega naught, multiplying a number by omega naught within characters is an S2 operation, a Z2 operation. You come back to yourself, mod n. We will see more as we go on because it's 1 mod n, right? 1 is identity. Okay, the second thing I want to tell you about this omega naught is that, and this is the key point, so lambda of r and minus s is equal to omega naught times lambda of r s mod n. So that reversing the sign of s is same as multiplying by this omega naught on lambda, on this integer lambda. Okay, that's the second claim. Now let's try to prove this. Okay. But to prove this, we just write this guy out. Okay, so this omega naught was p r naught plus p prime s naught. And lambda rs was equal to p r minus p prime s. Okay? Now, I want to see that this is PR plus P prime S. Okay? I want to see that this is PR plus P prime S modulo N. Okay? So we manipulate. Roughly speaking, what do we want to do? Roughly, we want to. Exactly. So we want to write this guy as PR plus P prime S, and then let's say minus 2 P prime S, because this gives us what we want here. And then maybe what we will do is fool around a bit. Maybe what we will do is switch the sign of this guy. So let's write this as minus or maybe this guy. I'll try one or two things. One of them will work. Let's try this as minus P. Huh? Uh-huh.
So if you write lambda RS as P R naught minus P minus naught times PR plus P prime S, that is lambda R minus S.
Say that again.
So write lambda RS as, write something like P R naught minus P prime S naught
P R naught minus P prime S naught
times lambda RS, which is P R plus P prime S.
Plus P prime S. Okay, so that you're saying the left hand side is this.
Yeah, so as Shivan said, you only need to worry about factors which are
Ignore non-cross terms, and those are the same, you're saying. Yeah, perfect. That's a great proof. Okay, I'll just say this again. I'll just say this in case. We want this quantity. But the argument suggested here is that the right-hand side is this quantity. The left-hand side is this quantity. It's this quantity because PR naught minus P prime S naught is 1. Okay? Now, right-hand side is not equal to left-hand side, but the terms which have P squared and P prime squared are the same because they come with P squared R naught R, P squared R naught R, and P prime squared S naught S, P prime squared S naught S. Okay? The terms that are not the same, have PP primes. And let's see that they have them with a factor of 2. That's all so let's take the difference between these two, this minus this. So we get P prime R naught S naught from here.
you get R S naught from the first.
RS, yeah, thank you. R naught minus R naught S. P prime, okay, I'll just write P prime. Yeah, I'll just write them all down. So this is minus R naught S plus S naught R, and then minus R naught S plus S naught R. Okay, so we've got a factor of 2. That term comes. Okay, fine. So we see that multiplying by omega naught on lambda up to things which are mod n, which doesn't matter because they don't matter inside K, switches the sign of S, and multiplying by omega naught again brings us back because omega naught squared was equal to 1 mod n. This was a consistency check because we know that if we reverse the sign of S and then reverse the sign of S again, you come back. So it had to be that this omega naught squared, at least in its action on lambda, was 1. And we see that that's the case. Okay? So, what we're going to do is to write this form, this thing as K of lambda minus K of omega naught lambda. Okay? And we will do all our manipulations first for K of lambda, and then very similar manipulations will go through for this K of omega naught of lambda. Okay? Now, the key point here though is that if you think of it as either as multiplication by omega naught or think of it as just reflecting the sign of S. Same thing. Once again, you see that you cut down the number of independent character functions by an extra half, extra factor of 2. Okay? Because the character is not by itself k. So let's write down the identity. The identity I'm going to write down. We have lambda chi of omega naught lambda is equal to chi of minus chi of lambda. This is obvious, right? Because chi was k of lambda minus k of omega naught lambda. So chi of omega naught lambda is k of omega naught lambda minus k of lambda, because omega naught squared was 1. Okay? And then it's just with a minus sign. So even though there were n by 2, roughly n by 2, independent values of k, there are only n by 4, roughly n by 4, independent values of chi. Because half of these independent values of k will give you chi's that are equal up to a minus sign. Okay? So as independent functions, there are only approximately n by 4 independent values of chi. If you look at the yellow book, it will do this n by 4 more carefully. P plus 1 by 2 into p minus 1 by 2, something, there's some more, or if you count it more carefully. You'll do that. I'm saying n by 4 roughly.
Can you repeat the argument? How did you get
This one? How did I get n by 4? Well, okay. We had first, in the range of integers, we had this lattice identification with n. So that's n. Now chi of lambda was equal to chi of minus lambda. That made it n by 2. And now there's this omega naught operation, which takes integers to other integers, under which chi is the same up to a minus sign. So that cuts it down by another 2. Now this 2 is not completely accurate, because there are some chi's which will just vanish. Because if lambda is same as omega naught lambda, then chi of that quantity is just 0. So you have to do the counting a little more carefully. Okay, but roughly by 4. Clear? Okay. So, and this number of independent chi's is precisely the number of independent characters which we get by the counting from last time.
Should I think of these characters in terms of, should I parameterize it in terms of RS or just lambda? There are two sets of things, right? RS or lambda.
Yeah. So RS had a certain excellent question. RS, it's the same really as Chintan's question, but let me say it more clearly. When we wrote down the set of independent characters, this when we worked it out last semester, our characters were parameterized by R, which went from 1 to P minus 1, and S, which went from 1 to P prime minus 1. And with the restriction that P prime S is less than PR. Okay? So you should think of characters physically as being characterized by R and S. But every distinct value in this range gives you a distinct value of lambda.
Two different set of RS.
Never give the same value. In this range, never give the same value of lambda. The ones that give are those that are related by the identities we've just talked about. Okay, there will be RSs such that they will shift lambda by n or something like that, and then give effectively the same value of lambda. But within this range, it's unique.
Yeah, so another question.
But let me just finish answering that question. Okay, therefore, within this range, you can equivalently label characters by lambda. Because there's a one-to-one map between values of R and S within this range and lambda. So it's an equivalent characterization. And I just wanted you also to see the n by 4 here. You see, if R was less than P prime and S was less than P, that's roughly PP prime, which is n by 2. And then that last inequality removes about half of them. That's the n by 4. Okay? Yeah, go on.
So when we wrote this chi in terms of k rs minus k r minus s.
Yes.
Why is there not a so there's a distinction between r and s, right?
Uh-huh.
As in you are just taking negative s.
Uh-huh.
Why not? Okay, so can we write a similar expression if we just switch r to minus 1?
Yeah, now, you know, we characterized our thing with two relatively prime numbers, p and p prime, and we chose some convention, p greater than p prime. Okay, so that breaks that symmetry. Okay, yeah, please go.
So this character of omega lambda being minus the character
Yes.
omega lambda, so the coefficients of these cannot be degeneracies anymore.
Exactly. And therefore, in actual appearances, you will never get an omega naught of lambda. So let me say, if you are within this range, you get a certain set of values of lambda. If you went outside of this range of R and S, then you would get a chi which was related to the allowed values,
Yes, okay.
okay, with a minus sign. Okay? So the fact that it's not really allowed is related to your statement. Okay? Though outside of this allowed range, that could not have been a character. Right? Within this range, we'll always have positive integers. Okay? Excellent. Other questions or comments? Excellent. Okay? So now that we've got the setup clear, now let's start doing the algebra. Okay? We've already seen how characters transform under tau goes to tau plus 1. That's relatively trivial. Next question, how do these characters transform under tau goes to minus 1 by tau? Okay? So as always, when we want to do these tau goes to minus 1 by tau transformations, what we want to use is a Poisson resummation formula. Okay, so let's do this systematically. So k lambda of tau was equal to 1 by eta of tau, and then sum q to the power, let me write it as e to the power 2 pi I tau times to the power n plus lambda by squared by 2n. Right? So now let's just by using definitions, we'll ask what is k lambda of minus 1 by tau. And therefore k lambda of minus 1 by tau is equal to 1 by 2 eta of tau. The sum is always over all integers. Okay. Sum e to the power minus 2 pi I by tau n plus lambda, the whole thing squared by 2n. Okay? Now what we want to do is somehow take this tau to 1 by tau. You know, this 1 by tau, we want to bring it up. And as we discussed at the end of the last lecture we had, a great trick for doing that is the Poisson resummation formula. This is a great trick because of the fact that the Fourier transform of e to the power ax squared by 2 is e to the power k squared by 2a. And the Poisson resummation formula basically asks us to take sum over function and replace it by sum over Fourier transform. Okay? So we will prepare ourselves to use this formula. So preparation using this formula, let's write this as this quantity as, so this 1 over eta of tau is out here, okay. Let me write this as eta of tau times. It's just, no, okay, fine. And then this will also have a, there was also an eta of minus 1 by tau. Okay. We'll deal with the eta of minus 1 by tau in a minute. So eta of minus 1 by tau times k lambda of minus 1 by tau is equal to, and now we'll write this as sum over at x equals all integers of e to the power minus 2 pi I by tau e to the power nx minus plus lambda, the whole thing squared divided by 2n. So this is the f of x the function that we're summing over all integer values. Okay? Now, this is the same thing as Fourier transforming and then summing the Fourier transform over all integer values. Okay? Now that Fourier transform has to be done with the right 2 pi. Okay, so for that I'm looking up the formula. Okay. So we do okay. Okay, so how have this guy's done it? Oh, what these guys have done, so maybe we write it like them. The sum over n is same as multiplying by e to the power I. Okay, I'm just doing it. Sorry, I'll get some 2 pi's wrong and then okay. So I'm just going to do it. Sum over all x with this. So now what we want to do is to do the Fourier transform. So let's take this f of x and Fourier transform it. Okay. So f of x is equal to e to the power 2 pi I by tau n x plus lambda, the whole thing squared, by 2n. Okay. So what's the Fourier transform of f of x? So what we have to do is to take this guy and multiply it by e to the power I k x. Fine. I think you're right about that. So once we do that e to the power 2 pi I k x, then we sum over all the integer values of k. I think that's right. Okay. So then we just have to do this, right? So this is e to the power 2 pi I overall outside, and then we have n squared x squared by 2n. So n x squared by n by 2 and by tau, 2 tau. Okay. Then we want the linear term in x. So that's plus n cancels, 2 cancels, lambda, and here we have k, lambda plus k into x. Okay, and then we want the constant term. Lambda by tau, thank you. Lambda by tau. And then we want the constant term. So the constant term is just lambda squared by 2 tau n. Okay, that's clear. Now we complete the square. So we write this as e to the power 2 pi I into, in order to complete the square, I will need an, I will add and subtract. So I will add lambda k square and lambda k square by 2 tau n. Okay, so n tau. Yeah, by 2 tau n. So when I do that, then this becomes a complete square. What was this? Lambda k squared by 2. So now I get the complete square. When I got the complete square, I do the integral. The integral gives me 1 over dx is like lambda, like tau. So I get square root tau. Lambda plus k, yes. Sorry, yeah, lambda plus k. All things square. So I get a factor of square root tau. Please check me. So I get a factor of square root tau by doing the integral, and so then I get square root tau times e to the power minus lambda plus k the whole thing squared tau by 2n. Okay? And then whatever was there before, which was plus lambda squared by 2 tau n. Is this correct? Do you guys agree with this? Sorry, nobody was following the algebra? I'm sorry. Can you please check this, because we'll get messed up if we don't. So I opened this out, completed the square, and got the integral. Do you guys agree that you get this? Okay. It's with an overall e to the power 2 pi I. Okay, I'm assuming that this is correct. Okay, so then finally what we're supposed to do, we'll take this square root lambda here, so we eta of minus 1 by tau by square root tau times k of lambda of minus 1 by tau is equal to square root of capital N. You're right, square root of capital N. Out here, you mean? Tau by n. So that's square root n, something like that. Yeah. Okay, thank you. This is equal to sum over all integers e to the power 2 pi I minus lambda plus k the whole thing squared tau by 2n plus lambda squared by 2 tau by n.
There should be some k square there, right, which cancels that k square. Your original thing only had k, right? We completed the square, there should be plus lambda.
I have that here, this k square.
Where did no, the original expression didn't have any k square, right?
The original expression didn't have any k square. So let's see. So what I did was I took this and I Fourier transformed. I did the Fourier transform by completing the square in x. Okay, so that required me to shift and get this additional term. All okay?
In this square,
There
there will be lambda by tau.
will be what?
Lambda by tau, rather than lambda.
Lambda by tau. Thank you. This is lambda by tau plus k. Thank you. Lambda by tau plus k. Okay. And now what? Sorry, just a moment. And this is now the point. The point is that the point is what? They had a factor of n. So have I messed up an n? Sorry, give me 1 minute. Everything that was 1 over tau for them came with a factor of n. Not seeing any n's here. First I messed up here because this was overall proportional. I'm so sorry for the incompetence. I'm so sorry for it. This thing was overall n square r nx plus No, this was okay. Sorry, they've got some extra factor of n which is sort of crucial to this algebra. Give me 1 minute. They get this k squared by 2n and with the tau exactly like we get. But this lambda maybe was that lambda? Give me 1 minute. There was also an n here, right? There was also, no, there was not an n, no. So sorry, it's 1. That was my n. Yeah.
I think your answer is right because if k was 0, then you should, it was already a complete square.
Uh-huh.
Right? So, since the second term comes with a 1 by n factor,
Uh-huh.
the first term should also come with a 1 by n factor.
Yeah.
Okay, then it will cancel.
Yeah. Give me 1 minute. See, the whole point is that we wanted this tau stuff, not this 1 by tau stuff. And I had expected everything that was 1 by tau to shift with n. Maybe that's not.
Lambda plus k as maybe k.
Give me 1 minute, please. Sorry. N. Okay. First, why isn't there an n here? K. I'm so sorry. They get finally k squared tau by 2n minus k lambda by n. That's it, up in the exponent. Are we getting the same thing here? Yeah. So we get sum over, which is about 2 pi I, and then just open it out. So k squared tau by 2n, okay, with a minus sign. Then minus lambda k by n tau. Oh, no tau, no. Lambda k by n, okay, fine. Then minus lambda k n by n. And then minus lambda squared by 2 tau squared n. By 2 tau n. Yeah, and that cancels this. Okay, so at least we get the same answer that they get. Fine, so they get this sum over k. I'm so sorry, I should have prepared more. Okay, so we get sum over k of this. And now what? Okay, excellent. Now what? Now what they do is the following. Okay, now what they do is to take this quantity and to write it as sum over k e to the power minus 2 pi I k lambda by n. Okay, that we have, times q to the power k square by 2n. Okay, that's just rewriting. This is e to the power 2 pi I, the minus sign maybe. You got the k square with a plus. Plus sign. K square with a plus sign. Okay, they got the k square with a plus sign. I'm going to assume the algebra gives us the k square with a plus sign. I'm so sorry about this. Let's just see how it works, at least assuming all this works. And then they say, well, they say let's write, and now this is now the key point. You see this point, this integer here is summed over all integers. Okay, so what we can do is to write this k as equal to mu plus m times n. So we have to sum mu from 0 to n minus 1 and sum m for over all integers. That produces the sum over all integers k. Okay? So let's separate out those sums. So if we write this as sum over mu is equal to 0 to n minus 1 and sum over m is equal to z, then we write this as e to the power minus 2 pi I k lambda by n. So this k is substituted with this mu plus mn. Okay? Now the first thing we notice is that this mn goes away because lambda was an integer and we have an e to the power 2 pi I shift. So this is same as here we have e to the power I mu lambda. Okay? And here we have q to the power mu plus mn, the whole thing squared by 2n. Okay? But this quantity here, if we go look back to that formula there, this quantity here up to this quantity here, this sum over the m's, is precisely that character with label mu. Okay? Mu is lambda, exactly. And so what we find is that up to getting the algebra correct, which I'm sorry about, what we will find is that we will get some mu's to the 0 to n minus 1, k mu of tau, and but with this weighting factor, e to the power 2 pi I mu lambda by n. Okay, now we have to deal with all those etas and the square root taus, but those work out. Those work out because we independently know how eta of minus 1 by tau is related to eta of tau. Okay, so those parts are separately, the square root taus are precisely what is needed to make those guys work out. Okay, so in the end we get a formula like this. It's like a discrete Fourier transform. K lambda of tau is equal to this. What? You want a minus here?
K lambda of minus 1 by 2.
Minus 1 by tau. Thank you. Minus 1 by tau. Minus 1 by tau. Okay, I'm sorry for the incompetence of the derivation, but I hope you see that if you sat down carefully, you could do it. Right? Okay. Fine. So let us believe that we have proved that k lambda of minus 1 by tau is this Fourier transform. The really key point here, just to emphasize, the really key point here was that in the Poisson resummation, we got a sum over all integers by n, but that the actual formula had sum only over shifts of n, integers modulo n, and therefore it became a sum over characters. Okay, with these coefficients. Now, very similar analysis tells you same thing for k omega naught lambda. Just repeating the analysis. Minus 1 by tau is equal to sum over mu is equal to 0 to n minus 1, k mu of omega naught mu of tau e to the power 2 pi I e to the power 2 pi I omega naught lambda mu by n. Okay, but and now we just change variables here. We just change variables. So I'll write this out again. So k of omega naught lambda of minus 1 by tau is equal to sum mu is equal to 0 to n minus 1. Sum over integers, z, k of omega naught mu tau e to the power 2 pi I. Then we have this omega naught lambda mu by n. Okay, but we now just club this omega naught with the mu. Okay, so this is nu times omega naught mu, and now this sum here is done over these omega naught mu's. Okay, and so once again the sum is weighted by whatever label came here times this factor nu. Where nu does this?
Omega naught mu is nu.
Just a minute. What was mu and what was lambda? Oh, this was, okay. So, this thing was here, k lambda, k mu, and we got mu lambda. So now we got k omega naught lambda. There is an omega naught mu times lambda. Yeah, times lambda. Now the sum is over omega naught mu. Okay? So whatever appeared here came here. And so in the end we find that chi lambda of minus 1 by tau is equal to sum over nu e to the power 2 pi I nu lambda by n chi of nu. Okay, that's the end result of this. Okay, we got something with this, and then there's something with the omega. Okay. So you might think that we've achieved our goal of trying to find the modular transformation of characters. Almost, not quite. Because you see, this nu was summed from 0 to n minus 1. Whereas you remember that the independent range of characters was about 1/4 of that. Okay? You remember that there are 4 identities. So of these chi's, not all are independent. We will have 2 of them being equal because they will be related by lambda and minus lambda mod n. And then 2 of them being then related with the minus sign because lambda and omega naught lambda. So now when you work this out carefully, you will get actually 4 different signs. Okay? You will get, once you put in all those identities and work only with the independent characters. Okay? Because we want to express the character at modular parameter minus 1 by tau as a sum over characters of the integrable representations. Right? Okay? So when we put all those in, so you'll get 4 terms, and these 4 terms turn out to be the following. You get chi lambda of minus 1 by tau is equal to sum over mu over all the integrable, all the actual representations that appear, chi mu of tau by square root n. And this had a 1 by square root n. This 1 by square root n was the 1 by square root n you guys pointed out in doing the integral. So this also came with a 1 by square root n. That just didn't go away anyway. Okay, so this 1 by square root n times e to the power 2 pi I e to the power 2 pi I lambda mu by n, and then plus e to the power minus 2 pi I lambda mu by n. This came from the n going to, the lambda goes to minus lambda. Right, there were 4 equivalences. 2 of them were lambda goes to minus lambda, and then the other 2 were lambda goes to omega naught lambda. Remember, omega naught lambda switched the sign of the character, so the other signs will come with a minus. So we get minus this one e to the power 2 pi I, and we get lambda naught mu omega naught lambda mu with an omega naught by n, and then we will get this guy but with lambda goes to minus lambda. So we get minus e to the power minus 2 pi I lambda mu omega naught. Is this clear? Okay? So this quantity, then which you can further process in various ways, gives you the S matrix. Now we have completed writing the character with after modular transform in terms of characters before modular transform. Yes?
So this tau going to minus 1 by tau, since it is giving us like the Fourier components of the initial wave, initial whatever character we are thinking. So can we say that these this tau going to minus 1 by tau is like in like double slit experiment? If you have a plane wave, you get some like Fourier components, right?
First, I don't understand why you say tau goes to minus 1 by tau is giving you Fourier components.
I mean, if you see this expression of character of minus 1 by tau, right?
You're saying because the S matrix acts by roughly a discrete Fourier transformation.
Yeah.
Okay, go on.
Can I say that this transformation is like in some space? I'm saying you have some slits, right? And then with this slits, you are making this transformation on your characters. Can we say something like that?
It's an interesting point. Yeah, I mean, roughly speaking, what you are saying is that imagine the characters as living at points on a lattice.
Yes.
And the tau goes to minus 1 by tau lives in momentum space on the lattice. The formula suggests something like this. I don't know if there's more to say about it, but it's true that it's a good analogy, that if we had a point on the lattice, if chi of tau was the position space wave function, chi of minus 1 by tau would be like a momentum space wave function. Okay, it's true that at that level it's true. Okay, excellent. Now, once we have this explicit formula, there are various ways of writing it in sines, cosines. It's clear already, right, that we have these two guys are cos, and these two guys are some other cos. Then you can fool around with it and write it in various ways. All that you can do. And point is, we have the answer. Okay. So we've got this S matrix. And now, because we got the S matrix, we can now try to address this problem we first set off trying to address. Namely, find the modular invariant pairings of characters and anti-characters. Okay. Now, one exercise one can perform, and it's given as an exercise in this yellow book, and I'll encourage you to try to do it, is by using this explicit formula, check that S has the following two properties. A, that it's a symmetric real matrix. In fact, that part is really clear from writing it as cosine minus cosine. So that part is one step, it's in front of your eyes. The second thing which takes a little more work is to check that it is a unitary matrix, or more precisely, that it squares to itself. Okay, so you understand, right? This thing, where is the matrix, some of you are asking? Well, the matrix is because we've got a quantity here. We can write chi lambda is equal to S lambda mu times chi mu sum over mu. Right? So these S lambda mu's are these coefficients. Okay? So these S lambda mu's are symmetric in mu and lambda, that's obvious here. They're real, that's obvious here. What's less obvious, what takes more showing, is that the matrix S squared is equal to 1. Okay? So a symmetric real matrix is its own dagger. So S square equals 1 is the same as the statement SS dagger is equal to 1. Okay? So this quantity here, just by explicitly looking at the it, you can just check that S square is equal to 1. This is the same as SS dagger is equal to 1. Okay? It's a little algebra with trigonometric functions, which I'll spend 40 minutes trying and messing up if I try. You guys can do it. Okay? Now, the fact that this is unitary, the fact that this matrix is unitary immediately tells us something very interesting. What is that? You remember what we did, what we were interested in was to find a pairing matrix P. Okay, so P chi dagger in matrix notation, chi bar, yeah, chi dagger in matrix, star and then acting from the other side. Okay, this pairing such that it was invariant under all modular transformations. But chi minus 1 by tau, chi of minus 1 by tau, one of the modular transformations, goes to S times chi. And so how does this P transform under this modular transformation? This tau goes to minus 1 by tau. You see, effectively P goes to S dagger PS. Right, because chi goes to chi, S chi. Therefore, chi dagger goes to chi dagger S dagger. Okay? So the problem of finding modular invariant pairings was the problem of finding something that was invariant under S and T. You remember those generate all modular transformations. You've done that, your end of the game. You already looked at T transformations last class. The T transformations were solved as long as this pairing matrix was diagonal. There may have been other solutions, but that was one solution. Okay? But we didn't know what those diagonal elements were. Now we know that those diagonal elements, or if not diagonal, other elements, are constrained to by this invariance condition P is equal to S dagger PS. Now can you think of one solution for this equation? Identity. Because S dagger S is identity, identity is equal to S dagger identity. Okay, so there is one very simple solution to for crossing. Now, note that identity is in particular diagonal, so it also is T invariant. So S is equal to identity is always a solution. Solution to modular inverse. Okay? So let's think about this for a minute. What does it mean S is equal to P is equal to identity? What it means is that every integrable, every allowed representation, unitary representation, left representation appears exactly once. And it is paired with its complex conjugate right representation. And that is the Hilbert space of the theory. Okay? So the Hilbert space of the theory is the product of every left and its complex conjugate right representation. Okay? The module of that representation with the complex conjugate representation summed over all representations appearing exactly once.
Can you say that again?
Okay. So what does it mean that S is identity? It means that every unitary representation is P is identity, sorry. P is identity. Every unitary representation appears paired with its complex conjugate and appears exactly once. So the Hilbert space of the theory is the module of representation A times representation A bar plus the module of representation A tilde plus representation A tilde bar and so on over all the representations.
A is like your lowest weight state.
A is yes, the lowest weight state, and when I say module of that, I mean all states built on top of that. So if I take the product module, it's an arbitrary state in the first module times an arbitrary state in the second module. It's a tensor product Hilbert space. So let me write that again. So the Hilbert space is in this theory over all representations. Let me call those. Okay, I'll call it RS. Chi RS, tensor chi bar RS, summed over these exactly once. Well, that's the Hilbert space of the theory. Okay? This Hilbert space is always, this is modular invariant. Now, in the last class, I told you that to be completely sure of, that all our constraints are being obeyed, we need to check modular invariance of one-point functions of tori. This I'm not going to do in class, but has been done.
Is it in the yellow?
I don't think so. Yeah. Yeah.
Can this thing not be chi RS times chi R prime?
What?
Like this Hilbert.
Can there be other solutions?
No, chi RS times chi R prime S prime. Chi bar R.
Well, if you do something completely random, certainly it won't work. because it will violate T invariance. You remember T invariance required that h minus h bar, or h bar minus h, which is actually the spin, it was an integer. If it was diagonal, that was trivially satisfied because h was equal to h bar. So you got the integer 0. In general, if you just do something completely random, certainly won't work.
So this solution that you are saying is because of your identity, that your P is identity,
Exactly.
you are writing this Hilbert space because
P identity is the same statement as that the Hilbert space is this. Exactly. Okay? So this always exists. That will work for T invariance, but will not work for S invariance in general. Because anything diagonal is good, it is T invariance, but it also has to obey this equation. And in general will not obey it. Choose an arbitrary diagonal matrix, will not obey it. Is this clear? Okay?
Is this unique because it's
Not unique.
there are like order dimension that metric dimension square constraints, but there are
Yeah, so you might have thought that it's a highly over-constrained system. So at first guess, you might have thought that there were no solutions. Well, there's at least one solution, so you should be suspicious. There are more discrete solutions. There are no parameter words of solutions. So in that sense, it's unique. Huh. Okay, so let's go to that question. What about the other invariants?
Sorry, what were the constraints? Like,
His question was that, right?
T n square constraint, but n variable.
Yeah, because P we know is a diagonal quantity. Oh, we're going to assume for a moment. Let's assume P is diagonal. Okay? Now Chintan asks, focusing on diagonal P, how many solutions are these? Well, we know S, some complicated matrix, we know it. And we've got as many equations as matrix elements in this equation. N square equations, n variables, you might think very hard to find solutions. It is very hard to find solutions, but there are a few extra discrete solutions. I'm going to tell you about some of them. Okay, though some of these leave the diagonal class. Hang on for a minute. Okay, now what else can you do to find solutions? Really, we will find all solutions when we study Wess-Zumino-Witten theory. Because using cosets of Wess-Zumino-Witten theories, we will find all modular invariant minimal models. Okay, and there's this lovely ADE classification which comes from this coset construction. What I'm going to do in these, like in the next 2 minutes, just tell you some vague things. Okay. One vague thing is this. We started by looking for diagonal P's. You might first ask, are there solutions which are not diagonal? Now, in general, if you had if h and h bar had been some arbitrary real numbers, clearly not, right? Because h bar minus h would not be an integer. But this is not in general. These HRSs are very specific things. So in particular examples, it could turn out that there are 2 or more HRSs which happen to differ by integer values. Okay? So one thing you can try to do is the following. You can group, given a PQ, a PP prime, group all HRSs that are in the same equivalence class, in the sense that they differ by integer values. Okay? Into one block. Group all the HRSs that mutually differ by integer values into some other block. And then it's not an ansatz, but then a theorem. Okay? It's then a theorem that this P matrix has to be block diagonal in these various classes. But it does sometimes happen that these blocks are not 1 cross 1 blocks. And associated with that, you do sometimes find these non-diagonal invariants. Okay? Again, we're going to study them systematically only later on. I just wanted to say that there do exist these non-diagonal invariants. Okay? Now, another thing Another thing that one can sometimes do to find more invariance, okay, another thing that one can sometimes do to find more invariance, from a matrix that obeys modular invariance, to try to find something that something more general that will also obey modular invariance, is a trick that we've already looked at before when we looked at fermions. Also when we looked at the orbifold theory. Okay? And this is another trick that sometimes gives you invariance. I'm going to tell it to you very abstractly, and then as we go on in our studies, we will encounter such examples. And the idea is this. Suppose our theory has a symmetry. Now, if you have a Lagrangian, you can from that Lagrangian see a symmetry. But if you don't have a Lagrangian, you might search for a symmetry of the fusion rules. So for instance, suppose you can find a Z2 symmetry. Namely, that you can take all operators in the theory and assign some operators as plus and some operators as minus, and check that the fusion rules respect this assignment with the Z2 multiplication rule. That is, fusion of plus with plus only gives you plus. Fusion of plus with minus only gives you minus. And fusion of minus with minus only gives you plus. Okay, if you can find such a grouping of operators with the fusion rules, okay, then as far as the operator algebra is concerned, your theory has a symmetry. Okay, now what you can try to do is to orbifold by the symmetry. Okay, what you can try to do is orbifold by the symmetry. That is, you can try to take this partition function, which in terms of the Euclidean theory involves all states and boundary conditions like this, and put twists here and sum over all twists. Okay, that operation sometimes also gives you new modular invariance. As I said, we will see examples of this as we go along. Okay, I just wanted to give you the basic idea here.
So those will be new modular invariants of the same theory because this is a discrete orbifold.
This is a discrete orbifold. So it's a new modular invariant of the same minimal models. It's the same operator spectrum, same fusion algebra, but it's a different operator content in the theory. Okay, we will see examples of this very soon within a lecture or two. We will see examples of this. Okay, so these. Well, I'll just finish the sentence. So these two. I think I've lost a mic. Okay. Okay. Okay, we're almost done with class, I suppose. That's a shame. Hello. Oh, there is a mic. Sorry. Okay. So these two operations are ways of giving you more modular invariance, and they can be combined together in various things. We will look at as we go along. We will look at both examples of this as well as a systematic classification. Okay, I'll just hold this. Go on.
Yeah, so with these block diagonals, you're saying we'll have extra constraints in terms of these if you want to your theory.
Yeah.
And then there will be sub blocks in these blocks.
Yes.
So is that the maximum that you can have, or like,
By doing this, there is a complete classification of everything you get. And one way of reaching many of these things is by looking for these blocks, searching for everything that will also then obey the S constraint, taking those, if you can find some, taking them, orbifolding them. Of course, everything that you will get will be block diagonal in the end, because it has to be T invariant. Okay, there is a complete classification and a way of getting all of these, but it's a bit complicated.
okay, so in terms of Hilbert space, you are basically having I RS times chi R prime S prime if H RS prime minus H RS is some integer.
You could have those, but that's not the only constraint.
That's not the only.
Yes. So there is a complete classification of all modular invariant partition functions of minimal models. This classification has this ADE, some group theory stuff, which we will see as we go along. Okay? The simplest of these is the diagonal invariant, this identity invariant. Okay? There are others, and we will examine them.
Very specific example of the.
It's a very specific example. Now, given a modular invariant and specifying the minimal model, that completely specifies your theory. It tells you what your operator content is. And you can compute all correlation functions. So the set of all minimal models is not just these PP primes, but that plus a specification of which modular invariant. Okay, those are all distinct theories. Okay, as I said, we will see examples of non-modular invariant, non-diagonal invariants. We'll see examples of overfolding very soon as we go on. Okay, more questions or comments? Okay, so I'll just take 5-10 minutes more. Okay, so this ends the first part of our discussion of modular invariance in these minimal models.
This board is not visible in the.
Oh no. Okay, what to do? Maybe you can turn the camera.
We can use.
Yeah, I can use that, but just so that that is on record. Okay. The next topic I wanted to discuss was the connection between this S matrix and the fusion algebra. Okay? In particular, the connection between the Nijks and the S matrix. So first, let me tell you what I mean by the Nijks. Suppose I take an operator phi I and do the OP of that with operator phi j. Okay? This guy can produce phi k some number of times. In order for this comment and the related question to be clear, let's look not at conformal field theory but ordinary group theory. In ordinary Lie algebra representation theory, if I have an irreducible representation, I take the tensor product of that with another irreducible representation. That tensor product can be decomposed into a sum of irreducible representations. Okay? Which representations appear on the right hand side? And how many times is a fundamental basic question of group theory. For instance, in SU2, if you have spin J1 and spin J2, in the tensor product, every representation appears either 0 times or 1 time. The representations that appear between 1 time are those between J1 and minus J. Let's say J1 is greater than J2. J1 minus J2 and J1 plus J2. The representations outside that range appear 0 times. Okay, so you might have thought that, there's a rule of group theory that every representation in tensor products appears either 0 times or 1 time, but that's not true. You go to more complicated groups, and sometimes the same representation in tensor products can appear 2 times or 3 times. Okay? So the question of, in the fusion of 2 representations, how many times does a third representation appear? Is a fundamental basic question of group theory. The answer to that question is always an integer. Okay? And so imagine for a moment that you were thinking of ordinary Lie algebra representation theory. You can ask how many times? How many times does this representation appear? Okay.
Explicitly, you can see this in like you take phi j OP, you get some integer times phi k with some normalizations to phi f. Like let's say normalize 2-point functions of all of them.
Are you asking ifCijk's are always integers appropriately? That's not true.
But then what does this?
It means the following. It means that if you take the direct, think in just Hilbert space. Take one representation and another, and now act with the full Virasoro algebra on this. Okay? Now break that tensor product up into representations of the algebra. Okay, yeah.
Like in terms of characters, you take product of characters and expand it as a sum of.
Exactly. Exactly. With what?
In terms of operators.
Is there a way of saying it in terms of operators? Right. It will be how many differentCijks there are. Okay? There are, let's say this in terms of group theory. Let's first ask it in Chintan's language in terms of group theory. What does it mean that there are two ways of getting representation K when you couple I and J to get K? What it means is that there are two invariant tensors, group invariant tensors, that couple the indices of I and J to give K. Two distinct ones. Okay? So in the same way here, there will be threeCijks. There will be as manyCijks. Okay? So in primary with primary gives primary, there would be distinct group invariant combinations.
How would you represent it? Like, how would you make it obvious? Like, CIJK, for different CIJKs, you're getting the same 5K something. You have to think that, right?
Okay. Let's ask in group theory. Okay. So suppose I've got some di alpha, dj chi, a. So the elements, so let's say that we've got some representation R1, R2, R3. The indices, the vector indices of representation R1 are chi1 alpha. The indices of this chi2 alpha, this are chi2 beta. Now, a coupling that gives you representation 3, and let's say that the indices of this guy are gamma. A coupling that gives you this is a C gamma alpha beta, chi1 alpha, chi2 beta, such that this combination transforms like a gamma index should transform in representation. Two linearly independent combinations like this, okay, will give you distinct. Okay? So that will be the same thing with these correlation functions. For instance, in a 4-point function, suppose we have phi1, phi2, phi1, phi2. If there are m different C's, if a particular K appears m different times, we'll get one conformal block, which is 1, 2, 1, 2, K, but there will be a m cross m matrix of such conformal blocks within 4-point functions. Because the 3-point function, the first 3-point function, you could have 3-point function of the first kind with some coefficient plus second kind with some coefficient and so on. And similarly on the other side. Okay? So it's these distinct ways of coupling that from the point of view of correlation functions label the number of. Okay? Excellent. So the number of operators that appear on the right-hand side is an integer. Okay, the number of distinct couplings, if you want, is an integer. And that integer we give a name. We have phi I with phi j, you fuse to phi k, and it appears nk times. We call that integer nijk. Okay? This nijk are called the fusion coefficients. Fusion coefficients of the theory. Okay?
What is some Cijk so that when the fusion appears, you know the multiple, that this time the multiple of thrice times Cijk is appearing?
Yeah, n is just telling you how many different Cijks there are. If you actually want to produce a correlation function, you have to know with what weight each of these representations is produced, and that's Cij. Those are the variousCijks. But these are just what exists. And then there is a question of how much they are produced.
Do you have to do this counting by hand? Like, you have to go around and do every phi ij and like see how many.
Even in group theory, I don't know of a general, maybe somebody knows. I don't know of a very general formula for these n's. In conformal field theory, the point of this lecture a point of what we are going to do, is to give you a relationship between Nijk and the S matrix. Okay? I'm going to give you a formula for n's in terms of this S matrix. So for instance, of course we already knew what n's were for the minimal models. But suppose you didn't, now that we've derived S, you will be able to find these fusion coefficients.
These fusion coefficients are independent of the structure constant.
The structure constant means Fijk? Yeah. Fusion coefficient. Meaning nothing's independent because the structure constant defines the algebra. And knowing the algebra, you can find the. So it's not, you can't change one and, I mean, they're determined, but it's completely different things. Yeah.
Just because you know what
We cannot, maybe it's determined.
case, but not in general.
Meaning one determines the other, so I won't say that you cannot find it, saying I don't know of a simple way of finding it. If you give me some too complicated representations of E8 and ask me how many times does the third one appear, I don't know how to do it. Maybe somebody does. Okay. Great. Now, let's go back to group theory. Okay. Let's go back to group theory and ask, suppose I'm interested in the following question. Suppose I'm interested in the question, how many different ways are there of producing representation, let's say M, out of the fusion of I, J, and N. Let's say I'll produce representation N out of the fusion of I, J, and M. Okay? So by fusing two, we had these integers Nij, K, which told us how many Ks we get by the fusion of I and J. But that was just with two. Suppose we want to fuse three. Okay? Then how many different ways are there? Well, you might think maybe we need some new integers, but that's too much. Because you see, tensor product can be done one at a time. So what we can do is first fuse I with J. So we get Nij K times so many Ks. And then you fuse K with M. Okay? So now what we're doing is fusing K with M. So we get NKM and N. And that's your answer. Sum over K. But then you could ask, well, hold on. Who told you I should fuse I with J and then with M? So let's associate a diagram with that. Okay? So let's associate a diagram with this. What the diagram I'm going to, I've got I fuse with J, I produce a K, I fuse with M, and I end up with an N. Okay, so this diagram denotes what I have done to count the total number of ways of producing K out of the fusion of I, J, M, N. But there's something else I could have done. I could have taken J and M, okay, fused them together, and then fused whatever the result of that was with I and got K. For instance, this is another thing I could have done. Okay, so let's see what we get when we do that. When we do that, we get Nj M, let's call this K prime, K prime, Ni K prime, this should have been N. Ni K prime N. That should also give you the same number of ways, because there's one answer, right? How many ways can you, in the tensor product of three representations, how many representations of something appears? There's just one answer to that question. Okay? And so we conclude that Nij K N Kmn is equal to n jmk prime n I k prime n. Okay, so this must be a true identity. Yes?
Can I not fuse I and M?
You can. You can. There's a similar such thing.
And is it like symmetric in Ij, Nij?
Yes, it is. Nij is symmetric because it's a question of when you fuse two representations, nobody tells you, there's no distinction between which these two. Okay. Now, I want to look here. In this matrix, this M here and this I here appear here, whereas this M here and this I here appear. So let's invent a matrix out of these coefficients. Let's choose any one of these indices to label which matrix, and then the other two indices to be the indices of the matrix. Okay? If we do that, because of the symmetry that Rajat talked about, we could write this as MK, KM, MK, same thing. Okay? No, whatever. Yeah. If we do that, this becomes, okay, so let's see. The final index here is n, and I will treat the final indices here to be j. So you see, both this becomes the statement ni n m is equal to n m n I as a matrix equation.
This I and M are like labels of a matrix.
Which matrix? Which matrix? I and M. You know, either one of these two you can choose as labels for which matrix because they're the same. The other index becomes a matrix index. I've chosen, in this equation, I've chosen this to be the which matrix index. This becomes the matrix index, J, K, K, N.
Is it something like the structure constants also in the adjoint representation concept?
This, you know, structure constants, it's a different thing. This is talking about how representations fuse. Well, structure constants are talking about the commutation relation of the algebra.
Yeah, but there also you have these three labels and then one is representing your...
Yeah. So in that trick, yes, I now understand your question. Yes, we use the same trick to promote structure constants to matrix representations. Yes, same trick. Out of those three indices, we make one of them to be which matrix, and the remaining two, yeah, correct. Okay, excellent, yes. Okay, is this clear? Okay, so if we adopt this notation, we can word the fact that you get the same answer no matter how you do the fusion as the statement that the fusion matrices commute with each other. Okay? But now everything I said about group theory goes through also for conformal field theory. I can just do this with OPEs. In the OPE of I with J, I produce some number of representations of K. You know, of those diagrams just go through. And the derivation goes through. So once again, in conformal, because it's just a question of representation. So once again in conformal field theory, we have these fusion coefficients, these Nijks. Okay? And once again, we proved that these fusion matrices commute with each other. Okay? Now, if matrices commute with each other, they can be simultaneously diagonalized. Please.
There should be more constraints, right? Like you could have used I with N.
I with N, yes. If we do that, yeah, it will all be like this. Let's try it. Okay, so we could have fused I with M, correct? Let us do it. So let's say we do I, M, and then some k prime, j and n. Okay? This is exactly the same algebra we've done here with m and j roles reversed. Okay? So what we will then get is that ni with nj is nj with ni. It's all subsumed within the statement that any two fusion matrices commute with each other. Is this clear? Okay. So now if a bunch of matrices commute, they can be simultaneously diagonalized. What I'm going to try to show you in the next class is that the matrix that diagonalizes them is the S matrix. The S matrix is the unitary matrix such that these n matrices can be written as U, D, U dagger, all simultaneously. Okay? And the U that does this is the S matrix. I'm going to try to show you that in next class.
So these end up like Hermitian.
These n are symmetric and real, so Hermitian.
So then the S matrix is always
Symmetric in the lower two, but in the
Okay, it's true. They're not completely symmetric, but almost. Up to this representation goes to complex representation symmetry. Yeah, so Hermitian, yes. Yeah.
so then this S is always unitary.
What? S is always unitary. We will also show this.
Is that Hermitian and they're observables?
They're certainly observables, but these are not operators on a Hilbert space. Yeah. Okay. Though of course they certainly, something we can compute, meaningful things. Okay. This was first observed by Verlinde, and then various people have given various proofs, none of which are very illuminating of this formula. But anyway, we will try to go through this discussion. So the connection between fusion and modularity is quite an amazing thing. No analog of that in ordinary group theory, because there's no analog modularity. Okay, we'll discuss this. Please.
P1 and P2 are two solutions to this.
Yes. Pairing matrix, yes.
P1 times P2 will also satisfy this equation, right? Because
Will P1 times P2. Let's check. Yeah, you're saying that, yeah, I think that's right. Because you're saying that S dagger P, S, P1, P2. We want to check, but that is S dagger P1, S, S dagger P2, S. Which was P1, which was P2. Yeah, I think that's right.
yeah, and this also works for T.
Louder?
This will also work for the T.
Yeah, this will work for every modular matrix.
So, I mean, what is that? Is it like taking tensor product here?
Well, it's a good question. So if we have two different diagonal pairing matrices, I don't think it's taking tensor product, because it's mixing things up, right?
Identity times identity is still identity.
Is identity, so that's trivial identities. Anything is. It's the non-trivial ones with each other that are non-trivial. It's a good question. It may have to do somehow with this orbifolding kind of thing. I don't know the answer. I'll see if I have anything to say. That's a very good point. That's a very good point. That may be a constraint. Yeah. So the identity should always appear exactly once. Yeah, that is an additional constraint, that the identity operator appears exactly once. And Omkar's point is that it may mess things up.
Identity is the coefficient of RX equals 0.
yeah, that is always like you just choose one for that.
So we have 1 alpha beta m. Now if we multiply this by 1 alpha prime beta prime m prime. What? If it's block diagonal, it's not obvious. Right. Yeah, if it's diagonal, that's true. But I think in general, Omkar is correct that there is a constraint from that. It's a good point. So that's not the only constraint. Yes.
So in theories in which having identity, like having a block diagonal with one in the first row,
Mhm.
I mean, where you're setting alpha and beta to 0,
Mhm.
that will happen only if, let's say, operators in the holomorphic side are, I don't know, they are not mixing with operators in the anti-holomorphic side. Right? That will happen only if that is the case.
Say it again. What will happen if that's the case?
You can have identity. You can have 1, 0, 0. You can have a matrix in which alpha and beta are 0.
Yes.
The way that you have written.
Yes.
That will happen only when operators in the holomorphic side are not mixing with operators in the.
By mixing, you mean pairing.
There is no pairing
Between identity and something that is purely anti-holomorphic. Yeah. Yeah. But of course, we know of theories where this is, for instance, del in any. Thank you. For instance, del x by itself is a good primary operator in a free boson theory.
Yeah, that is fine. But you want the dimension of all those holomorphic operators to be integers.
To be integers, exactly. So they would be like currents and so on. Right? And that's the case for del x, for instance. It was dimension 1.
But will that happen in minimal models? Because the dimension of these operators were like something like r e prime minus e prime 3 prime e r squared minus something by.
Yeah, you're saying for minimal models, maybe it will always be the case that these are 0. You're asking, is it ever the case that, yeah, well, we already know that dimensions, well, okay, can be quite large. Okay, I'm not sure. The question is, do these things ever become integers? Okay, again, to which I don't know, somebody knows, but it's both points are good points. That naively it works, and that there is one additional potential constraint on this. Yeah. Okay, good. Other questions or comments? Okay, next time.